Now, so everybody once again listen this part. So in the previous sessions we have discussed about operational amplifier, about the IC here like this. That is, you can see here the basic op amp, okay, open loop gain and equivalent circuit, ideal conditions, okay, and once we study this op amp, okay, with this ideal conditions and equivalent circuit, then we start then we have started here about inverting and non-inverting and difference amplifier. That is, when you try to use the op amp will be used basically in three modes, okay, that is inverting, non-inverting and difference amplifier. How do we classify this in sense? If you try to give input to the inverting and ground the non-inverting terminal, then we call this as nothing but inverting amplifier. You try to take you try to give the input to the non-inverting terminal and ground the inverting terminal, then we call that as non-inverting amplifier. Suppose if you give inputs to both the op amp terminals, then we call it as difference amplifier. So you try to use the op amp, basically whatever functions you do, okay, definitely you will use the op amp only in these three modes, okay, any one of these three modes only you will be using it. Next, apart from this, we have the characteristics of the op amp. That is, this is AC characteristics and DC characteristics, okay, AC and DC characteristics. This we have already discussed. Now, so if you try to look here in this part, AC and DC characteristics, how we have studied for BJT biasing and H parameter model as AC model, like that we try to study the op amp also in the AC and DC conditions. For that, we don't take here any H parameter model and try to analyze all those things now, because it is a IC biasing. We don't do anything for that transistors which are present inside the IC, because already the manufacturer will take care of the entire biasing part. So biasing will be done perfectly inside the IC. Once that is done, okay, there is no interference, okay, in that regard. That is the reason. So we try to study the DC characteristics as offset values. What do you mean by offset values? Means when the manufacturer has provided biasing properly, now there is nothing for us to do. The moment we try to give AC input, definitely you are going to get an amplified output at the output terminal. But practically what will happen is you will find some errors. That errors we call them as offset errors. Okay, offset errors means when I don't give input, still I will be getting some output, okay, due to various reasons which we have discussed earlier. Okay, so due to that reason, when you try to get like that errors, that errors has to be compensated. For that reason, we study the DC characteristics as input offset, okay, voltage, output offset voltage, and input offset current and input bias current. So these are the topics which we try to study, okay, in the DC characteristics. So once you set the offset characteristics properly, then there will be no problem with the op amp. It will try to give you, okay, this offset error has to be corrected externally. One has to remember this. This offset error has to be corrected externally, using a source. Okay. Now, so by doing like that, once this error is overcome, okay, once this error is overcome, now left out one what you have is only AC characteristics. Okay. Now this AC characteristics is about when I try to give AC input signal for different values of frequencies, whatever I am giving, okay, the op amp should work for all the range of frequencies. But the op amp will not work like that practically. Ideally we say, but practically it doesn't work. Practically there is a limitation for certain range of frequencies. If you cross that range, then the op amp gain is going to fall down. Okay, so then I understand that the bandwidth of the op amp is limited, it is not infinity. So I cannot meet ideal condition. So within that range only, I am supposed to operate the op amp and try to get the required result. Now, so about that we try to study it as AC characteristics here. Now, so these are the amplifiers these are the topics what we have studied earlier in the case of op amp. Now, so next one what we have is applications of op amp. Before getting into applications, now just let us try to look at one part here, that is difference amplifier. Okay, that is inside the op amp. two important topics are there where there is a great chance for you to get gate questions in this area. Okay, that is difference amplifier and current mirror. Okay, these two are the areas where we need to concentrate. So let us try to study now the difference amplifier. Okay. Now, differential amplifier, that is the op amp, how it is working as differential amplifier means, because we are using two emitter coupled, okay, emitter coupled differential amplifier, okay, we try to choose. Now, how this emitter coupled differential amplifier is arranged, let us try to see here. Now, everybody try to see here. So, do not copy this diagram. These changes will be there in this diagram. Now, you try to see that the difference amplifier here has got a power supply from this point VCC. But what the story here is that an op amp has got, okay, some basic terminals, that is an op amp, or you can say difference amplifier. Okay, the difference amplifier is given with two inputs, two power supplies, two power supply, minus VEE plus VCC, and two input terminals, one output. Now, everybody can see here, this is V01 and this is here V02. V output is equal to V02 minus V01. Okay, the design will be like this. The output should be taken from V02 to minus V01. Okay, you will be taking it like this. Now, if it is so, now let us try to see here. The IC current comes here and IC current comes here. Okay, now in this case, the transistor Q1, okay, and Q2, when they try to design, Q1 and Q2 are identical. Identical in sense their AC parameters, DC parameters, everything will be same. Alpha, beta, gamma, okay, functions, and their HIE, HRE, HFE functions, everything will be same. So, like that only they try to design it. So, in spite of taking care, okay, for this design, some variations will occur in manufacturing. At that time only we get offset errors. Okay, if there are no variations or identical manufacturing is done, there is no problem at all. Okay, comfortably you can use this IC. Now, during this process, but however you try to take care, okay, some errors occur because of mismatch in the transistor. That only we try to overcome externally using offset pin. Okay, fine. That is about the correction if they are there. Now let us study this circuit. We have to study this circuit now. So to study this circuit, because VCC is common to both and RC is kept equal, and it has to be kept equal for sure. Okay, then only it will work as perfect differential amplifier with high gain. Okay, RC of both the transistors are equal, transistors are equal. Now what is going to vary is inputs only. VS1 will be different from VS2. Okay, these are the only parameters which will vary. And this is the source resistance and this is the source resistance. The op amp is nowhere linked to this. Okay, so now you can understand that this RS1 belongs to source, okay, and RS2 belongs to source. So don't worry about this point. So these parameters are kept constant. Now what happens is, why I need to connect minus VEE? Earlier we were connecting only one source plus VCC. We did not connect minus VEE here. Okay, we did not connect this, but now we are connecting this, isn't it? So when you try to connect minus VEE source here, why we should connect? Now let us see. If you put here 0, now you see the wonder of this circuit. Now, if you try to say, for example, let us try to see why we should connect minus VEE source here. Suppose that if I try to fix here, VI equal to, okay, VI2 equal to 4 volts. This is fixed. Okay, this is fixed. Now, if I try to connect it directly to the ground, okay, now this value will be 0. Suppose let me give here 2 volts. So 2 minus 0, okay. 2 minus 0 equal to 2. So this junction will be forward biased, base emitter junction. VBE will be forward biased. Okay, and here if you try to take VBE equal to like this. Now here I need to take 4 minus 0 equal to 4. This is also forward biased, no problem. It will run. But I told you that if you don't have RE resistance at this position, okay, if you don't have RE resistance at this position, then what will happen is that this circuit is not going to, okay, it will not have stability. It will have high current gain, but stability will be poor for this circuit. Okay, to have stability, what we need to do here is, you need to put the RE resistance. For having stability, I try to put the RE resistance. Now, on putting the RE resistance, carefully see here, on putting here RE resistance, now what will happen is, the current coming from this is IE1, current coming from this is IE2, and current in this is IE. Now let the arrangement be like this, IE equal to IE1, okay, plus IE2, okay, like this. Now let this currents be here, the sum of these two currents be, okay, 1 ampere, 1 milliampere, say, okay. Let it be 1 milliampere. If you give more voltage, definitely you will get more value. Okay, or else you can consider like this. The current coming from this, because it is 2 volts, current coming from this is less, and because it is 4 volts, current coming from this is more. You can consider it like that. But the sum of these two, let us say for example, is 1 milliampere. Okay, say now when it is 1 milliampere, now let the RE value, okay, RE value will be equal to, say it is 2K. Okay, let it be here 2K. Then what will happen here is that, okay, take 1K here, okay, take it 1K. Now VE voltage is equal to IE into RE. So 1 milliampere, 1 into 10 power minus 3 into 1 into 10 power plus 3. So what is the voltage I get is 1 volt. So this is here 1 volt. Then I'll get here now 2 minus 1 is equal to 1. Okay, and here I'll get it as Okay, like this you will be taking the difference of these two. Now what happens, you try to see. I say that this is fixed and I have an option to change this voltage from 0 to maximum. So I'll try to increase this voltage to 4 volts. Okay, I'll try to increase this voltage to 4 volts. There is a rise in this voltage. Okay, when this VI voltage is equal to 3 volts. Now this is forward biased. Because I have made this now more voltage, this junction is more forward biased. When the base voltage will increase, obviously IB current increases. IB current increases, thereby IC increases, IE also increases. IE is equal to IC. So you can see here that because of increase in base current IB, okay, because of increase in base current IB, IC current also increases. If IC increases, IE also increases. Now in this manner, if IE increases, say the IE value has increased, say the IE value has increased to 3 amperes, okay, 3 milliamperes, then I am going to get this VE value like this. VE is equal to 3 into 10 power minus 3 into 1 into 10 power 3. Now I am going to get this voltage here as, so 3 into 1, 3 volts, okay, 3 volts. Now here I am going to get this value 3 minus 1, still this is forward biased and this is also forward biased, no headache. Okay, now if this voltage is further increased from 4 to 8 volts because of increase in this voltage, okay, now once again current increases and current becomes say 6 milliamperes. Sum of IE1 plus IE2 is 6 milliamperes. If it is 6 milliamperes, now then what will happen is that now 6 into 1, you can see here, now it is 6 volts. Okay, it is 6 volts. Now at this situation, you can see here that now 6 volts is equal to minus 2. Now this is reverse biased. Okay, now 4 minus 6, this is equal to, okay, sorry, I'm sorry, 8 minus, I'm sorry, let me put it properly, 8 minus 1, okay, earlier, okay, we thought, earlier it was 1, okay, so assume that it is 1. Now, so once I have increased this voltage, it becomes 7. Now it will no more be 1 ampere here. Why? Immediately it will become VCC because this transistor is off. IB is 0. As IB is 0, IC is also 0. So therefore, you will find V output equal to VCC. When this output goes high, immediately like this, okay, this is what I was telling. The op-amp when you try to operate, okay, the op-amp when you try to operate can work as amplifier only between certain range of voltages, that is plus Vx and minus Vx. If you try to cross little bit also voltage about that, quickly it will go to saturation at sold. This is because of this reason. You can see that this transistor did not disturb this transistor, okay, it is no way involved with this. This is operating its own inputs, okay, and this is silently sitting with fixed value, okay, but what happened, you see, when I try to change the voltages at this transistor, immediately this transistor has gone to cutoff region. Okay, like that, without touching this transistor, I am able to operate this transistor functionalities also. Okay, that is the greatness of this, okay, circuit and weakness of this circuit also, because I did not expect this output. Okay, but it is giving me wrong output. That is, I did not ask this transistor to go to cutoff, but just I am operating only with this transistor, but this transistor output has gone to cutoff. Okay, that is the point you need to observe. So as you like, whatever inputs you want to give, you cannot give for op amp. You should definitely be within the range of input signal. Control this. Okay, due to that reason the outputs will definitely fluctuate. Okay, you should be careful in operating these two conditions. Next, observing this point here, VCC, carefully observe. Okay, when this voltage goes high, this voltage will be definitely less than this voltage. Now no doubt about it. So the difference what you are going to get will be definitely a high voltage. It will not be a low voltage value. Okay, so keeping this point in mind, if you try to observe like this, then at any moment during operation, when you try to give input signal, one of the transistors may go to cutoff region, or they may be going to saturation region also. They don't go to saturation, they go to cutoff here. Okay, because of that reason, what happens is you should operate the transistor, you should operate the op amp within the limited region. Then that becomes difficult task. Why? Because I have wide range of input signals when I want to give it to the op amp and get the signals to be processed. Okay, so the only option what we have is this RE must be, this transistors must be controlled such that even though my input signal varies, all of you listen carefully, even though my input signal varies, the swing increases and decreases to a great extent, this transistors must not go to cutoff. That is the reason what we do here is we try to now connect the VE source, like this, with the help of resistor. With the help of RE resistor. Now current through this is named here IE1, current through this is named IE2, IE is equal to IE1 plus IE2. Now what happens is, because I am putting a negative source here, whatever I try to do, whether the inputs here change or don't change, whatever it may happen, whether this RE voltage, let it change, no problem. Let it change, no problem. Because I am putting here minus VE, this voltage will be very less, that is negative voltage. Because of that reason, both the transistors, never they will be driven to cutoff region. Now there is a chance to get control. This is what is the purpose. Now they have studied and they have put the minus VE source here. So now the question is very simple. What happens if I don't use minus VEE? What happens if I don't use minus VEE? If I don't use minus VEE, then definitely the transistors may be thrown to cutoff region during operations of the input signal. That is the point. Now, so this is one point you need to observe. Now later on, what they have observed is, after putting minus VEE also, now the new problem will start. That is, one problem we have overcome. That is not allowing the transistor to go into cutoff region. That problem is overcome. But never it will go to cutoff region. But the new problem is, on putting minus VEE and RE resistor also, the voltage at the emitter is not stable. Please all of you note this point. After giving this minus VEE, the voltage at this node VE is not stable. It will increase and decrease. Why? Because this point, carefully observe, based on variation of base signal here, this currents IE1 and IE2 will vary. Here if variation occurs, IE2 varies. Here variation occurs, IE1 will vary. If these both are varying, then IE will vary. If IE varies, then voltage in this RE also will vary. When it varies, what will happen here is that now you will not have stable operation. This is the problem. Due to that reason, again the transistor may go into cutoff region. Now again it may go into cutoff region. Why? Because we could control the transistor not to go into cutoff region only to some extent, but we could not maintain here VE voltage constant. This VE voltage is not constant. So because this VE voltage is not constant, what happens is output will not be stable. That is the problem. Okay, output will not be stable. So how to make this output stable? Okay, means you have to control the voltage in the RE resistor. How do you control the voltage in RE resistor? IE into RE. RE is constant. IE must be controlled. Okay, IE must be controlled. Okay, so to control IE, now we need a constant current source. Okay, we need a constant current source. So let us try to study about this point, constant current source. Now, in order to maintain constant voltage VE, IE must be maintained constant. Okay, IE must be maintained constant. Okay, this is done by two ways. This is done by two ways. The first method is constant current source. Second one is current mirror. Current mirror. So we try to do it in two ways, constant current source and current mirror. Okay, when you try to observe these two carefully, everybody, okay, what happens here is that this constant current source initially was the circuit or first circuit which was used, but this circuit has got a problem that because of the Zener diodes used and ordinary diodes used and the transistor used, as Zener diode or ordinary diode which is used has got dependency of current value on temperature. So when temperature changes, then immediately the performance of this diode and transistor currents also has changed. Due to that reason, okay, this circuit could not will not be able to produce constant current value. Okay, due to that reason, this has become a flop model. Now, so instead of using this, okay, we try to use, okay, current mirror. These are also called as active loads. We call these two as active loads. Okay, now, so when you try to look at this point, the current mirror, okay, now this circuit is most popular and we try to use this current mirror in place of constant current source, because this could not serve the purpose completely, okay, because of its variations in parameters. So we try to go for the current mirror circuit. Now let us try to look at the current mirror circuit here. Okay, now this circuit. Okay, here there is an indication that a lot of care will be taken in selecting this Q4 transistor. Okay, Q3 and Q4 transistors are identical. Okay, are identical. Here IB3 will be equal to IB4 and IC4 will be equal to IC3. Okay, both will be equal. IC3 will be equal to IC4. Okay, and both parameters HFE and rest of all parameters will be equal, and VBE4 will be equal to VBE3. So this junction voltages also will be same. So this, because you are selecting the identical transistor, this is how it will be same. Now you see here, all of you carefully, what is the important story here is, this current what you are finding here IC3, this current will be equal to this current. Okay, if you bring any changes here, okay, this current, immediately I current will change. Immediately I current is going to change. Okay, one should understand this carefully. Okay, see the logic how this circuit works. Okay, now what current you have here IE, all of you see here. Okay, what current you have here IE, this current will be, is nothing but, okay, IC3 here, IC3 here. Are you getting it here? So this is going to be here, the functionality here. You are going to connect it here. Why? Because you can connect it to the active load part. Okay, so this we are going to connect it like this. Now let us try to see here this functionality for this. Now the current equation what we write here is I is equal to I1 plus IC4. I1 is plus IC4. I is equal to break. One 150 1 mega ohm potentiometer is connected in series with RB. Determine range of possible values for VC for the network using potentiometer. Okay, so 1 mega ohm you are saying. Okay, and already you have connected 150k, right? So if you try to observe that, then you change RB into 150k RB into mega ohms, that is multiply by 10 power 3 divided by 10 power 3, then you are going to get that is 0.15 mega ohm, okay, plus 1 mega ohm, because you have connected 1 mega ohm potentiometer in series with RB. So add those two, so then it becomes 150, that is 1.15, okay, 1.15 mega ohm. Okay, it doesn't make much difference there. Okay, okay, so you can take it as approximately 1 mega ohm and calculate it. Please try to see once, Saloni, the problems which I have solved exactly with the same numericals in the classroom. I have taken it 4.7k. okay, RE I have taken 1k and VCC 12 volts. I think beta I have taken 100 or 120. Okay, now you try to take the same problem there. Okay, see the solution of the classroom problem what I have solved. Okay, still I'll give a hint here. Okay, try to look at this. That is, IB will be equal to, okay, VCC minus VBE divided by RB plus beta RE plus 1 plus beta into RC. So this is IB. You will get here IC is equal to beta into IB. Okay, beta into IB, and VCE equal to VCC minus IC into, okay, RE plus 1 by beta into RC. So this is the output voltage equation. So this is here VCE, right? Now you want VC, isn't it? VC is written here as VC minus VE. Okay, VE can be written as VC minus nothing but IE into RE. Okay, then you are going to get the answer. So this is the answer, okay, for VE. So I can get it like this. VE equal to plus VCC minus IC into RE plus 1 plus beta into 1 by beta into RC. Right? Here for RB you should take it as 1 mega ohm plus 0.15, okay, mega ohm. This is RB given, and this is potentiometer what you have. Okay, this is potentiometer what you have. Take RB value, sum of these two, and dump it in the formula, you get the answer. Okay, so this is the question you have. Next, Saloni from Ahmedabad. In voltage divider circuit, R1 R2 equal to 50 VCC is 18 volts, VE is minus 18 volt, RC is 1 K, and RE equal to 7.5 K, beta 130. Determine IB, IC, VCE. Okay, very simple. Only small difference you get here is, that is VE is given in that circuit. Given minus VE. This is the only difference what you have. VCC. Okay, R1, R2. So this is connected to ground. Okay, so you can now please try to understand like this. You take like this, ground. So this is here RE. Just write KVL for this problem. Okay, just write KVL for this. This you have given 8 volts or 18 volts. Okay, and VCC is given also 18 volts. Okay, 18 volts. I doubt this circuit whether it will work or not. Okay, now, so no problem. Still you can take it. Now please try to write KVL for this loop. Okay, KVL for this loop. Here you should take current IE. Okay, and you should replace this with Thevenin equivalent circuit. Okay, so like this you need to write. That is, you please note down when I am writing here. Okay, this is R Thevenin, this is V Thevenin. Okay, and this is the circuit here, and you have here minus 18 volts. So you can ground this here. So for this circuit you write KVL. Don't write here. If you write here you will not get solution. Write here. Okay, write the KVL here, and this is here RE, IE. Current in this must be taken as IB here. Okay, this is R Thevenin. Okay, now here RC will be there and VCC will be there. Now please write KVL for this and KVL for this. Okay, you will get the answer for all the details what you have asked. Okay, right. Or you can look to the problem which I have given, same model. Okay, I have solved it in the class. Right. Next, Sanjeev Bilaspur. How this current mirror circuit is substitute of RE where minus VEE and IE in Sanjeev, I have not completed the topic. Okay, if I complete the topic what I am teaching now, then you will understand how it will be a compensation. Okay, right. So please have patience. I request all students to have patience. Okay, I am going to definitely complete and teach you what is written here. Okay, try to be a little bit patient. Next, Mayank from Bangalore. Sir, I have missed BJT classes. Can I cover it in FET classes? Almost the analysis you can cover it, but you need to understand that FET is a voltage control device, whereas BJT is a current control device. As far as equations, circuit diagrams are there, both will be same. You should be just be careful with KVL equations, what we write there and here. Okay, that is the only thing you need to remember. Okay, fine. Next, Avinash from Kota. Sir, how does RE resistor makes common mode gain? How does RE resistor makes common mode gain small to increase CMRR? Okay, so this I will be able to tell you now, but not at this moment. Why? Because let me complete this, then you will understand what is the importance of this. Then how RE resistance can improve the CMRR, I will be able to tell you later. Okay, next, Arun from Salem. In transistor Q4, Avinash, it's a good question what you have given. Arun from Salem, in transistor Q4, IC and IB is given same current. Will there be not any problem? IC, Q4 IC and IB is given same current. Q4 IC and IB is given same current. Not at all. You can never say that these two are same currents. Why? Because the okay, let me come to the explanation point, then I'll be able to tell you. Okay, because half knowledge is dangerous. Let me complete this. Next, Shruti from Delhi. I'd like to know how the power of MOSFETs are structurally different from normal MOSFETs. How do they conduct large currents? Wonderful question, Shruti. But did I teach you MOSFET till now? Okay, let me come to the point. I request you, wait for the topic. See, try to ask questions with the relevant topic, so then I can explain more and help you more. Okay, when I come to that MOSFETs, you try to pose this question, then I'll be able to tell you. Sir, in transfer characteristics of op-amp, due to what factors does practical op-amp has deviation? Okay, there are many factors. Temperature, biasing, noise, okay, and the power supply voltages. Okay, so all these factors will try to affect, and most importantly, VBE voltage across the transistor. This is the main parameter which is going to disturb the transistor, VBE voltage. Next, Ashutosh from Bhilai. Sir, as per your last class explanation about offset, I found practically a minimum value of 1.53 volts, but not full zero all the way I tried. So there is any other configuration of it. I appreciate you, Ashutosh, because you have done it practically also. That's very, very good. Okay, what you need to do is, you are speaking about offset. Which offset you need to let me know, or else if it is voltage offset, you have to compensate it. If you are not getting zero, you have to compensate from plus terminal as well as minus terminal, both. Then you may get zero. That is one option. And if it is input bias current option, you should connect R compensation resistance to non-inverting terminal. Okay, and if you connect that value and put that value high resistance, then you can get, there is a chance for you to get zero. Okay, this is one option you have. Or you need to put a T network as a feedback from output to inverting input terminal. Okay, by selecting proper values of resistance. That is one option you have. Okay, so you can try with this, then you are going to get perfectly zero there. Right. So next, Aman from Delhi. When one transistor of op-amp goes into cutoff, then output should be VCC minus V01. Yes, it is true, but V01 is varying. So output V01 is varying. So output should vary. Yes, it will vary for sure. But what happens is V01 value, when you compare with VCC, that will become very small, because that signal hardly it will come to 1 volt. VCC will be given nearly 15 volts. Okay, so due to that reason, the transistor will have great chances to get into saturation very easily here. And this output what you are giving will not be the final output. It will go as input to differential amplifier of next stage. Then you are providing just providing very, very high voltages to the base of next stage. When you give that much high base to the next stage, immediately the next stage transistors will go to saturation. they will not be in cutoff also, they will try to go to saturation. When they go into saturation, then that output voltage is nothing but plus VCC, okay, or minus VSAT, okay, minus VCC. So quickly the transistor will go to, okay, a non-linear region from linear region. So you are looking at only this circuit, what is there on the board, but this output will be connected to input of the next stage. As this output is a high voltage variation, that if you give to the next transistor, base will become more, transistor will go to cutoff region. So it is very difficult to manage, okay. So that is the reason we should understand that it is not advisable, okay, if you need to maintain this RE voltage, you should maintain it constant. Next, Nicey Calicut, sir, please suggest reference book of op-amp. Already I have suggested Sergio Franco, Linear Integrated Circuits by Rai Chaudhary, okay, or you can refer Sergio Franco or Cedar Smith. These books are good. If you look at Cedar Smith, is excellent. Still in industry, it is considered as the best book. If you are not able to understand this, I'll try to suggest other books. Next, Saloni from Ahmedabad. In that collector based bias circuit, you took RB as 1.15. From this, we get one answer. But how can we decide range of VC from this? It's very simple. VC can have only two options. Either it can become VCC. Okay, either it can become equal to VCC or it has to become 0 volts. Okay, 0 volts. Why? Because less than 0.3 volts, transistor will go to saturation. That is the point you need to remember. Right. So you need to make a correction like this. Now let us continue with our topic here. So based on this here, okay, that we are replacing this circuit with this. Okay, all of you observe here, there is no VCC, please. No VCC. Okay, there will be no VCC here. Okay, now do correct it. If I have written here VCC as explaining the transistor circuit, for current mirror there is no VCC. Because this part you are going to directly connect it here. Okay, remember it, no VCC. This part of RC, what you are seeing, okay, directly you will take it and connect it to this point. Okay, and this RC resistance will act as RE resistance for this amplifier. Okay, remember it. Now, so let us try to see here this point. Now, I can write here like this. Now, you try to see this current I is equal to, okay, I equal to I1 plus IC4. So, you can see I equal to I1 plus IC4 here. Now, once you have this here like this, okay, I1 plus IC4, okay, what will happen is, you see, what is I1? Carefully see, I1 is IB3 plus IB4, okay, I1 is IB3 plus IB4, I1 is IB3 plus IB4, okay, now plus IC4 I have here like this. Now this, everybody try to observe here. Now I can write this circuit, okay, I can write this equation like this. I'll write this as 2IB3, okay, 2IB3 plus IC4 or, okay, or 2IB4 plus IC4. Okay, like this or like this I can write. Why? Because I am selecting these two transistors same. These two base currents will be same provided their base voltages are same. Now all of you look here carefully. This node and this node both are at same potential. There is no drop here. So this node voltage, what you have at this point and this point, is nothing but voltage across this resistance. So I can name this as VR, and here also it will be VR only. Okay, both will have same voltage. Okay, right? Now, so if this is VR, observe carefully, the Q4 base is connected to VR and Q3 base is connected to VR. It means Q4 base voltage and Q3 base voltage both are same. If both voltages are, that is both inputs are same, then definitely IB4 and IB3 must be equal. That is the reason we have written it like this. Okay, if these are equal, instead of writing IB4, I can write here IB3, or I can write twice of IB4 plus IC4. Okay, like this. Now I can write this equation once again as, carefully see, 2 into IB3, carefully observe, 2 into IB3 plus IC3, because IC4 is equal to IC3 equal to IC4. Okay, I'll get it like this. Now one can question here that how IC4 is equal to IC3. Try to understand here, everybody, carefully try to understand. If these two transistors are identical and their base voltages are same, then what will happen here is that this base voltage will decide IB4 and IB3. If IB3 and IB4 are equal, okay, then definitely beta of these two transistors are equal, then definitely IC4, what you get, IC4 is beta into IB4, IC3 is beta into IB3, because beta is same and IB are same, definitely this IC4 value and IC3 values are also same. Okay, and try to remember here, all of you try to see this IC4, mention, please concentrate everybody, this IC4, okay, is not, okay, dependent on this current, remember it. Okay, this IC4 is not dependent on this current I, it is dependent on IB4. The collector current is not dependent on this, okay, I, it is dependent on IB4. IB4 will decide IC4. Okay, now, so this is transistor current direction, so we have represented like this. That is the reason we could write the KCL like this. But I is not becoming this part. Okay, now, so please don't confuse with this, how from ground I get current. Okay, you just wait, I'll be able to tell you now how this current comes. Now try to see from this point. So everybody note that IC4 is not coming from here, it is coming because of IB4. IB4 is coming because of this voltage. Okay, carefully observe. Now, so once I try to write this, now I hope everybody understood this point. The collector currents of these two transistors are dependent on the base currents. Base current is dependent on VR voltage. VR voltage is dependent on this resistance voltage. Okay, now try to see here. I is equal to, like this I try to write. Now carefully see, IB3 means what? It is nothing but IC3 by beta. Okay, IC3 by beta is equal to IC3. Now you try to take here IC3 common, then I get here 2 by beta plus 1. Okay, 2 by beta was plus 1. Beta is much greater than 2. Okay, beta is 50. Okay, 2 divided by 50, 1 by 25. So 1 by 25 is 0.004. Okay, 0.004. So there is no use of it. Okay, so 1 plus 0.0025 is of value. Okay, negligible. So neglect it. Okay, hence this term is neglected. Then I get here IC3. Now you all of you observe, this is the equation we have here. Okay, this is the equation we have here. Now carefully see here, I is equal to IC3. But observe in this diagram, what a wonderful adjustment, okay, current mirror does. Whatever change you make in this resistor, okay, whatever change you make in this resistor, that changes will occur here. And whatever changes you make here in this resistor, okay, current resistor, not in the resistor values, current, okay, resistors are constant. Now whatever changes you make here, this IC3, whatever variations are there, the variations of IC3 will be reflecting in I. Carefully observe, the variations of IC3 will reflect in I. Okay, because of this reason, carefully observe, if this IC3 changes, then I changes, voltage in this resistance changes, voltage in this resistor changes, VR changes, then immediately IB changes, okay, IC4 changes and IC3 also changes. It means now you try to get more current. Okay, you try to get more current from the emitter. Okay, this is the emitter. If you get more current from the emitter point, okay, like this, from this point if you try to get, this current is nothing but this current. And this current, if it varies, immediately the reflections will be seen here. and this voltage will vary. As this voltage varies, immediately the base voltage of these two transistors varies. Then immediately this collector current will vary, this collector current also will vary. Then immediately you will have a change here, okay, in this current, and this current will be once again controlled. This current will be once again controlled. So this current is going to control this voltage is going to control the currents. Once again this current will be controlled, okay, from this point again. If any change occurs, immediately the deflection is going to come and attack this current once again. So the changes in currents will be nullified, okay, from this point to this point, and so it will be maintained constant, okay. Now as this current reflects, this changes in this current reflects here, and changes in this current will change the voltage here. This reflection again reflects here. That is the reason we call it as current mirror, okay. We are calling this as current mirror. So this circuit will be replaced here in place of this here, okay. Now, so this is the point one should understand, okay. Now, and you try to see here that this emitters here will be connected with the negative power supply here, okay, and you need to form a loop here like this. All of you carefully see, you need to form the loop here like this. When this is connected, when the entire section is connected to this point, okay, all of you carefully see how this current I comes if you ask, okay. Then if you bring that circuit and connect it here, this entire loop, if you try to consider along with current mirror, it forms one loop, and that loop is going to give the current here I. That is how it comes. Now one has to refer the text, okay. Now here, this differential amplifier is operated in two modes, okay. This differential amplifier can be operated in two modes here, that is differential mode and common mode. In CMRR we have seen differential mode and common mode, okay. So when you try to take the differential mode and common mode here, okay, the amplifier is designed for differential mode operations. So it is not supposed to operate in common mode. Wantedly we also don't do that, but due to the arrangement of the circuit and the common inputs which we get, such as noise to both terminals, which is common, plus and minus, okay, there is a chance for us to get common mode gain also. In such case, we try to reduce the common mode, okay, common mode signal, and we try to have more amount of difference mode signal only. For that, we try to have the CMR value, okay, CMRR value should be kept very high, okay. How it is kept high? Let us see here. First, let us see the operation mode and then come to that point. Now, for that, now this circuit which we have differential mode, okay, differential amplifier, okay, differential amplifier is operated in four configurations. The first one is single input, balanced output. Next one is dual input, dual input, balanced output, and third one, single input, unbalanced output, single input, unbalanced output. Next, dual input, unbalanced output. These are 4 configuration. What do you mean by this single input balanced output means? Like this we try to take here, and we try to take this point also like this. Okay, if you take here V01 and V02, okay, V01 and V02, carefully observe. If you take between, if you give only one input, Vi, I give, and I make, this is V1, okay, make it V1. V2 is 0, this I ground it. This is single input, okay, and the output if you take it like this, V02 minus V01, okay, V output is equal to V02 minus V01. Then I call this as single, okay, this is the circuit, that is single input, balanced output. If you take output between the collectors C1 and C2, then it is called balanced output. If you take between collector and ground, it is called unbalanced output. Okay, so now you try to get it for this case like this. Dual input, it means both inputs you will give, okay, both inputs are given. Here V1 is there and V2 is also there, both inputs are given here, and I try to take here output V01, V02. So V output equal to, and this you can put it 0 here, okay, V02 you can put it 0. Now here both will exist, V02 minus V01. So this is here V02 minus V01. It means because of input you get output, because of this input you get output. Now difference of these two is the output. So this is called dual input, balanced output between these two. Now for this single input, okay, only single input, V1 is there. If I take between these two terminals, V01 and ground, so this is here V01, okay, V01 and ground, so I need to take it between ground. So this is here unbalanced output, okay, these two here are balanced output, okay, between these two terminals if you take. Okay, next next you need to give input for both, that's it, and both outputs you should take it from ground only with reference to ground. Okay, so now it will be like this. So between the grounds if you are trying to take, it is unbalanced output. So here now you can see this point. 9.02, 9.99. You will be getting different values like this. Why? Because those are called floating values. When the grounding is not done properly, okay, you will not get accurate results. When you do ground it, definitely it should be 0 here. Then only you will get proper values. So as it is very difficult to ground the values, okay, in the normal circuits what we do, that is the reason they are called unbalanced outputs. Okay, so in 4 different configurations we try to operate the op amp here. Okay, the first one operating modes is difference mode, common mode gain. Our aim is to amplify the make the op amp work as difference mode, and we should not operate it in common mode. But unfortunately we are forced to, that is the situation during operations force us and we get the results as force the op amp, not us. Okay, it will force the op amp to have common mode gain also because of the noise signals. So when these two come, you will be getting the differences like this. Okay, now here, now we should know this op amp. Now we have the differential amplifier. In the differential amplifier, for the differential amplifier, as it is amplifier, obviously you have to make it work as make it work in active region. When you want to make it work in active region, then the biasing is important and AC behavior is also important. Okay, so this here you need to do some derivations for this. Okay, because both the emitters are coupled here, okay, and you have RE resistance and all this, what happens is that when you try to couple them like that, the analysis cannot be done, H parameter analysis cannot be done in the normal way how we have taken it. Okay, it has to be replaced by T network. Okay, for this T network, and the combination of these two emitters must be coupled. Okay, and that becomes a complex analysis, and you'll be getting 3 loops. Out of the 3 loops, you have to write mesh equations and solve all those things. So instead of struggling like that, okay, I'll try to put here the formula. Okay, simple here. Now you try to note down the formula for the DC analysis and AC analysis of this op amp. In GATE, you need not study this analysis of differential amplifier. Only try to know the formulas what is required. The explanation what I have given, that is important. You will get questions in that area. But now for DC and AC analysis, no derivation is required. Just try to take this formula here. Now for DC conditions, now DC analysis of difference amplifier. DC analysis of difference amplifier. So take one transistor out of 2. Okay, take one transistor out of 2. You get here IV1 will be equal to VEE minus VBE whole divided by 2 into beta RE plus RS. Okay, this is here I have IB1, and you know that IC1 will be equal to beta into IB1 DC conditions. Okay, and this value you can rewrite it like this. Once again, you can substitute that formula of IB1 here and find out the value of IC. Okay, it becomes very simple. So IC1 you can rewrite it like this. IC1 Q is equal to VEE minus VBE whole divided by 2RE and VCE Q, that is operating point, VCC plus VBE minus IC into RC. Okay, that is ICQ. ICQ into RC, like this. Okay, this is how you are going to get this term. Okay, VCQ. Now, these are the DC conditions we have here. Now, I am erasing this picture here. Now, we should look at AC conditions. Now, the AC analysis part. AC analysis. Now, in the case of AC analysis, you are going to get the gain here. That is, in AC analysis, what do we study? Input resistance, output resistance, current gain, voltage gain. These are the factors. So, now you are supposed to find these factors and voltage gain. Because op-amp is used as voltage amplifier, we try to find out voltage gain only here. We don't bother about the current gain much. Okay. Now, so let us try to look here. What is input resistance for nothing but 1 by GM. Okay, so you will get it here. This is nothing but VBE divided by, okay, IE. So VBE divided by IE. This will be given. Now, so now you can see here, this is the formula, very important formula, okay, for the differential amplifier. When a differential amplifier is given to you, if you keep on writing KVL and doing all AC analysis, H parameter analysis, you will never get the answer. It will become 2 to 3 pages of information. In exam, you are not supposed to do like that. You need to remember that, okay, RE value will be given to you in the question itself. In the RE value will be given to the, okay, in the question itself, he will give you the details. Just take the beta of that circuit and multiply it with this. That's it. Directly you are going to get the, okay, RI value here. Now, so this is here, ohms. Next, input resistance. Output resistance is nothing but here. Only RC you are going to get for this. Okay. And you have another formula for RI also. Like this also, you have R. RS plus HIE. There is another formula, okay, or if this is not there, this you get, but this rarely you get, okay, this we generally don't use, we try to use this only more, okay, by both means you will get same answer only, okay, right. Next, output resistance R0, R0 will be equal to, okay, R0 will be equal to RC, so output resistance. This is output resistance. Output resistance equal to RC. So this is gain, which we consider here it as difference gain AD. Okay, that is AD, difference mode gain. Okay, AD will be equal to HFE RC divided by RS plus HIE. Now, so how do you get in this AD? It is very simple. V output by VI. V output is what? difference mode gain, what we get? Ri is now nothing but Rs plus HIE. Okay, this is what you get. Now, the next most important point, now common mode gain. So, one of the student has asked this, how Re will reset, okay, how Re is going to correct the common mode gain. Now, dear student, look at this formula, 1 plus HFE plus Rs plus HIE. Rs plus HIE. Okay, so this is what you are going to get it here, and make this Ri here 2. Ri is equal to twice. Okay, 2 into Rs plus HIE. Make this Ri 2 twice here. Now, so all of you see here from this point, okay, now this parameters carefully see. So the common mode gain formula, okay, is this one. Difference mode gain formula is this one. So in exam, when he will give you a differential amplifier and ask you find common mode gain and difference mode gain, then you should not solve anything. You are supposed to remember this formula, no doubt. Okay, so then you have to remember this formula. There is no option. Now, or else you have to struggle with the entire derivation, which you cannot expect to do in exam. Okay, 2 to 3 pages. So the difference mode gain is dependent on these parameters. Common mode gain is dependent on these parameters. HFE RC. Okay, now 2 RE 1 plus HFE into Rs plus HIE. Now all of you please see, okay, how I differentiate between common mode gain and difference mode gain. Please look at this point. If I remove this part, okay, if I remove this part, carefully see, the common mode gain formula is nothing but nothing but difference mode gain. Okay, in difference mode gain, what I am getting it, right? In common mode gain, why I have to take this Re? Because if you remember the formula of input resistance with Re, CE amplifier with Re only, if you remember that, then there you will get as HIE plus, okay, HIE plus Re into 1 plus HFE. This is the formula of input resistance. So input resistance, current gain into RL dash, AI into RL dash divided by Ri. This is the voltage gain formula. Whether it is common gain, common mode or different mode, formula will remain same. Now, as emitter is common to both terminals, okay, if one terminal of the differential amplifier is taken care, still the from other terminal noise can enter, or any common mode signal which is there, that also can enter. So then as this noise enters, now this becomes common to both, okay, and this will reflect at IC. If both common signals reflect at IC1 and IC2, then they will reflect at IE1 and IE2 also. So sum of these two has to be considered here. Okay, as input resistance, when IE1 and IE2 are also affected, then input resistance will be affected. So input resistance is dependent on Re into 1 plus HFE. Therefore, this is the reason, okay, you are going to get here this Re factor like this. Now, so if this Re is there, if you increase Re, carefully listen, if you increase Re, common mode signal will be reduced. Okay, common mode signal will be reduced. This is what one of the students were asking. Okay, how common mode signal will be, okay, controlled. Okay, how CMRR will be controlled. Okay, if you increase Re, AC will reduce. AC reduces, CMRR increases. Okay, that is the point you need to remember here. So here you get CMRR. Okay, CMRR is equal to, okay, AD by AC. Okay, as Re is increased, AC decreases, okay, CMRR increases. CMRR increases. This is how we can control CMRR with the help of this. And this derivation, this is very simple. This is not a big derivation. Normal derivation already what we have done. Okay, for all those circuits, same. current gain into AI into RL dash by RI. Okay, from that we try to get it. So this is the point which we learn here. Now I am erasing this part. Now you can take here one more important point. Okay, the AD is also calculated like this. Okay, AD is equal to V output by VD. Okay, one more important point. This is obtained by 1 by RE. Okay, so this is also one more formula for finding. Okay, that formula or this formula you can use. In terms of HIE, if you HIE details are given in the question, then you have to use this formula. If RE is given in the details of the question, then you have to use this formula. Direct, very simple. Okay, take the collector resistance and take the details given in the question value of RE. If RE is not given, RE equal to VBE divided by IE. Okay, so any of these values will be given to you, definitely for sure. So using that you can calculate RE, or if RE is given, the job is more simple. So you can take it like this. So this is the point you need to remember here. Now, so like this, for each of these circuits, okay, for each of these circuits now, you will get the gains like this. Please all of you see. For single input, dual input, single input, okay, unbalanced, okay, you are going to get the values like this. That is here, AD will be equal to RC divided by RE. Here also AD will be equal to RC divided by RE. That is for balanced. But for unbalanced, the gain is going to be reduced. AC divided by 2 RE you are going to get. Here also AD will be equal to RC divided by 2 RE. So for unbalanced, you have gain like this. Okay, this you need to see here. Okay. So for unbalanced, you are going to have the gain like this. Okay. You need to remember these points, very, very important. Single input, balanced output. Okay, dual input, balanced output. It means whether it is single input or balanced output, understand from here itself what is the importance. Whether you use inverting or non-inverting terminal, still the amplifier is going to op amp is going to work as amplifier and the gain remains almost same. Okay, that is the reason what all inputs we will give. Now itself you try to remember, when the op amp is operated in linear region, okay, all the inputs are given most of the time to inverting input terminal, that is minus terminal, and plus terminal is grounded. Why? Because feedback will be provided to minus terminal. Okay, because of that reason stability will be more. So you can see that whether you give inputs to both or single, when it is balanced, you need not worry because the ground is not there. So the gain remains same whether both are there or not. When you try to give single input, okay, unbalanced case, the gain is going to be reduced because here, now when you try to ground, the feedback currents will increase, which will increase the resistance in the path. Due to that reason, when input resistance in the path increases, whenever you provide feedback, okay, the input resistance in the path will increase. Because of that reason, the input voltage will decrease. As input voltage decreases, obviously the gain of the amplifier will decrease. Because of that reason, you should get this AD is equal to RC divided by 2RE. You can observe this here, unbalanced case, because you are connecting it to ground. Additional loops will be formed when you connect to ground. the additional loops will be found. But between 2 points are C1 and C2, collectors of both differential amplifier you take, the additional loops you don't get. So that is the reason the factors will be restricted. So due to that reason, here gain will be more, here gain will be less in unbalanced case. So this is about differential amplifier and its AC analysis, DC analysis, and its configuration, differential amplifier configurations, okay, and what you call the gain factors, okay, what we have seen just now, and how this is going to affect. These are the points we need to remember here. Now I am erasing this part. I am erasing this. Now the next topic we have here is we get into applications, okay, and we get into applications part here, and one can note here regarding the CMRR what you have written here, right. Let us take a break and come back. Same in BJT and FET. Yes, biasing and AC perfectly they are same. Equation, everything will be same. Instead of IE, you will have IS. Instead of IB, you will not have IB. You will have IG, but IG is always 0 because FET is voltage control device. It is given reverse bias, so IG is always 0. In place of IC, you will have ID. In place of VCC, you will have VD. And rest of KVL equations, everything will be same. Just if you can change the names in the circuit, that is enough. Only point you need to remember is IB should be replaced with 0 because FET input is always reverse bias. That is the reason you will not get input current there. There is no input current for FET. Okay. Next, Avinash Kota. Sir, I have read at high frequency, coupling capacitor has 0 value. At high frequency, coupling capacitor has 0 value. Emitter bypass circuit has negligible value. Explain. Okay, Avinash, just now I if you have done so, please verify once like this in the lab, you will be able to do it. Next, Ajay from Jammu. In linear region of operation of transistor, B junction is forward bias. Is dependent on very small base current IB. It is the one-way function. If you see the H parameter model, we have written here like this. Okay, we have written the H parameter model like this. Okay, HFE IB. This is here IC. This is here IB. Okay, now like this. So this on this small current will control this large current. Okay, all of you see here, if you have a transistor, Okay, VCC, IC here. This part of IC, what you are seeing, this RC will not control this. Okay, RC cannot control IC. RC cannot control IC. IC is dependent on IB. Remember this point very carefully. Okay, so from this point you should understand the dependent, this is current dependent current source. Okay, that is output current is dependent on input current. If you say that this is from this side, then we should take one dependent source here like this. Okay, we should take dependent source, current source here like this, but we are not taking like this. Okay, that is the reason we should not, okay, think like that. So it is not in the reverse. Okay, fine. Next, Dinesh from Mumbai. Sir, what is GM for a BJT? Okay, GM is nothing but transconductance. You need to take IC divided by VCE. That is what is GM. But you try to take it in a different fashion here. Okay, like this. Now, so IC will be equal to, okay, minus IC will be equal to GM into VBE. Okay, so GM will be equal to minus IC by VBE. This is called transconductance. Okay, for BJT, transconductance. In high frequency analysis, we learn not here. Okay, this is about the transconductance. Now, so this is the point you need to remember. Fine. Now next, see the CMRR we have learnt, what we have learnt earlier. Okay, all of you try to see the CMRR. Now some important point I'll try to tell regarding this. Already we have learned this. Okay, some part of equation you try to understand how CMRR will be maintained high. Okay, for that what we need to do. Now you try to see CMRR, the ratio of, we take it as the ratio of, okay, difference mode gain to common mode gain. The ratio of difference mode gain to common mode gain is called CMRR. So for this what you 1 plus, I rearrange this, okay, VC by VD into, here I rearrange it as VD divided by, sorry, AD divided by AC. AD divided by AC. Okay, when I try to write like this, AD divided by AC is nothing but CMRR. Why we say CMRR must be high? Because all of you can see here now by VD. If CMRR is high, okay, if CMRR is infinity, CMRR is equal to infinity, then you get V output equal to AD into VD, because this becomes 1 plus 0. So V output, now the op amp will work as a differential amplifier. Okay, this works as difference amplifier. So why CMRR should be high? Okay, now why CMRR should be high means, this is the reason. V output equal to AD into VD. This works as a difference amplifier. Fine. Now, so the last point, let us see slew rate. Okay, one important formula for GATE exam. Okay, so on slew rate you need to know the slew rate functionalities and its important formula here. Copy this quickly. from this point is, now the amplified form you get it here like this, okay, perfect output, or you can say no distortion. No distortion. But what happens now, you see, frequency is increased. Now the input signal frequency is increased. If you increase the frequency, now the variations you can see here. Earlier in 1 second, if you have 2 cycles, okay, in 1 second if you have 2 cycles here, in 1 second now you have many cycles here. It means 1 second 2 times it will change. In now here for 1 second many changes are there. Then the op-amp transistors also should respond very quickly. First stage differential amplifier, second stage differential amplifier, level shifter, and the output stage. All this should change very fast. Okay, if they are not able to change fast, then what will happen is output will be delayed. So then your output will be distorted. You will get the output like this. That is, so now this is distortion. Okay, this is because the inability of the op-amp to respond to quick changes of input, we call this nothing but, okay, the what you call the transistors or transistor stray capacitance characteristics, okay, gives this response. Okay, due to this, what reason we'll see now. Okay, if I try to give a step signal for this, okay, like this step signal, then the output of this circuit, it will be like this. This is distortion. Square wave or step signal when I give, you can see here, now there is a distortion. You can see the gap here. Okay, you can see the gap here. The same distortion occurs in this case and in this case. Okay, square wave. Why? Because, okay, this op-amp has got BJT inside, and that BJT which is there has got PN junction. Okay, has got PN junction. All of you can look here like this. This is one resistor. This is one resistor. Forward bias RBE, okay, RBC, reverse bias here and forward bias here, and this is one junction I have here. Okay, this is CBE, and this is here, you get here CBC, right? This is called here, okay, diffusion capacitance CD. This is called transition capacitance CT. That is, a diode under forward bias will exhibit diffusion capacitance, under reverse bias it will exhibit transition capacitance. Okay, what happens is that because you have a capacitor, it will have storage time. So due to this storage time, it will not be able to respond quickly from, okay, changing its output due to the transient behavior of the circuit. Okay, due to the transient behavior of the circuit, what you find here is that now, okay, what you find is that this charging behavior, everyone please note it. Okay, note it, very, very important. Okay, the internal capacitor of transistors, the internal capacitor of transistors, I repeat, the internal capacitors of transistors produce transition and diffusion capacitance effect, transition and diffusion capacitance effect. Due to this, storage time, on time, off time of transistors, on time and off time of transistors Okay, the charging of capacitor does not take place. The charging of capacitor does not take place quickly. Does not take place quickly. As there is a delay, therefore the output is also delayed or distorted. The output is also delayed or distorted. Full stop. Next point. Okay, in order for a good op amp, slew rate should be very, very high. Write fast. Write down these points. These are very, very important. Quick, 2 minutes. Okay, the slew rate of a op amp should be very, very high. The slew rate of op amp should be very, very high. Okay, for this action, the current rating should be very large. The current rating should be very large. The current rating should be very large. In bracket, charging of capacitor. In bracket, charging of capacitor. In bracket, charging of capacitor. Full stop. Okay, this is given by. Now take this formula. Slew rate is equal to I max divided by C. Okay, maximum current, okay, to be given, okay, for having, okay, for having required slew rate, okay, I max is equal to slew rate into C. Next, maximum frequency of input, signal, okay, to be given such that there is no distortion, okay. FM, maximum frequency, is equal to slew rate divided by 2 pi Vm. Slew rate is equal to 2 pi Vm. So you should understand that this op amp has got a limitation. As you like, any signal you cannot give. You should give the signals only with limited frequency. And what is the maximum frequency of the input signal for the op amp to work without distortion means, okay, so, okay, this is the maximum frequency. F max is equal to S divided by 2 pi Vm. Okay, this is the formula. Vm means maximum peak voltage of AC signal. Vm is equal to peak voltage of AC input. Okay, fine. Now we end the session today. We'll continue tomorrow. Tomorrow we'll discuss about op amp applications.